Hello, everybody. Welcome to class. All right. Good morning. Happy Friday, week 3. So just a couple things to keep in mind. Sorry, where's my list here? 1 second. Okay, you guys are fine. Sorry, I thought you guys had an exam coming up. You do not. It's my other class. FAM's class has a midterm May 8th. Sanders, you guys are just doing quizzes, so just be aware of that. Oh yeah, of course, I'll share it numerous times, but yes, there you go. And something else. No, oh, I posted the solutions to the second quiz that you guys took. So if you have any questions, you can go look at that. If you still have questions, you can always ask me. And I think that's about it. So I figured we would talk about limits today, but I guess before we get going, I should ask, is there any specific things that you would like me to talk about today? Okay. Well, hearing no requests from the crowd, I will do some limits. And so when it comes to limits, there's a few things to be aware of. Oh, difference equations. Oh, sure, we can do that. We can do that first. Yeah, definitely. Yeah. So just so you guys know, I did do an example. I posted a video yesterday of where you find the limit of a difference equation, like the one in the homework. So that's definitely something you should go look at. I'll do a different example right now. So I think we're moving toward talking less about setting up the difference equation and more towards just evaluating it. Here's the link again. But you could, yeah, squeeze theorem, sure, definitely, on top of it. All right, so difference equations. They might ask you to still set it up, although that it gets kind of weird. We could do something like, I don't know, it's for this to be what I want it to be, it's not going to work out very nice. So let's not do that. Let's say this is our difference equation. Let's say a sub n plus 1 was equal to 4/5 of a sub n plus 7. And the idea, and maybe it doesn't really matter where you're starting, but let's say we were starting at, oh, I don't know. Sorry, I'm trying to make the numbers work out just a little bit nicely. Sorry, my brain. Just 1 sec. Really, that? I don't know, whatever. Let's just say a sub 1 equals 5. And so while you could find more values, right, like you could say, okay, well, if a sub 1 is 5, a sub 2 is 4/5 times 5 plus 7, which is 4 plus 7, which is 11. And then a sub 3 would be 4/5 of 11 plus 7, which is not very nice, right? It's 44/5 plus 7 is 35/5, and you get 79/5. And then you plug that back in, and you keep going. And so the question becomes, sorry, here's the attendance one more time. The question becomes, what's the limit of this recursive equation or difference equation? I usually call it a recursive equation, same idea. And so what we can say here is that, well, if you're taking the limit of a sequence, sorry, it's a little bit bright now. Taking the limit of a sequence, it doesn't matter if you're taking the limit of a sub n plus 1 or the limit of a sub n, right? If your sequence is some terms, just for a different example, like if b sub n is the terms, I'm going to use what I did from the quiz. I should mirror my video. Sorry, things are looking weird to me. One moment. So if you remember the quiz, I asked you to look at this sequence. It was 1/2, 2/3, 3/4, 4/5. It was the sequence given by n minus 1 over n. Or maybe it was n, then it was n over n plus 1. Same thing, but starting at a different place. Sorry. Right, so there's b sub n. And here's b sub n plus 1. It's n plus 1 over n plus 1 plus 1. Right, if you're finding the n plus 1 term, you're just plugging in n plus 1 for n. And so if you look at these, both of these sequences have the same limit. It doesn't matter if you go one term further. If you let the terms go to infinity, this thing and this thing are both going to go to the same place. The limit of this is going to be 1 because it's a rational function, and the degree on top is 1, the degree on the bottom is 1, and the quotient of the leading coefficients is 1 over 1, which is 1. But the same thing is true over here. If I rewrite this, this is n plus 1 over n plus 2. And that also has a limit as n goes to infinity of 1 for the same exact reasons. Sorry, there's like birds outside my door here. They're loud. Paul, I know, I'm sorry, I'm getting distracted. Okay. So, doesn't matter if you're doing this one or this one. So the point of this is that the limit as n goes to infinity of b sub n is the same as the limit as n goes to infinity of b sub n plus 1. And we're going to call it, we usually call it capital L. And so what I'm going to do here is I'm going to take the limit of both sides. Now, here's what we're really going to do. When you take the limit of everything, what we end up getting is you just plug in capital L wherever you have an a sub n or an a sub n plus 1. Here's why. I take the limit of both sides. Well, the limit of a sub n plus 1, we said the limit was L, so I'm just going to write capital L. And the limit of this, I can use my limit rules and say, oh, well, the limit of 4/5 an plus 7 is the limit of this plus the limit of that. Right, using the limit of the sum is the sum of the limits. And I'm going to do a couple things. I'm going to bring this 4/5 that's a constant out in front. That's one of the rules as well. The limit of a constant times a sequence is the constant times the limit of the sequence. And then I'm going to write this as 4/5 times, well, the limit of an is L. It's going to be 4/5 L plus the limit of a constant is just the constant. So when you're finding the limit, or sorry, when you're trying to find the limit of difference equation, you basically just replace each of the a sub whatevers with L. And then you solve for L. So L minus 4/5 L equals 7. 1L minus 4/5 L is 1/5 L equal to 7. Multiply both sides by 5, and L is equal to 5 times 7, which is 35. And that would be the limit of this sequence. Sorry, no, that's fine. Yeah, that's the limit of the sequence, yes. The problem is sometimes you get more than one L and it's not always the limit. So he'll hopefully talk more about that later. For now, it's fine to just say that's the limit, but really this is what's called an equilibrium point. And it's a value that could be the limit of the sequence, but if there's more than one equilibrium, you could have multiple ones. So I'll show you another example, and then I will also give you the attendance score one more time, or I will try to. Sorry. One more example. Let's see, our difference equation was a sub n plus 1 equal to, let me come up with something good here. a sub n plus 3. Sorry, 2 over a sub n plus 3. That works fine, yeah. And let's say a sub 1 is, let's say it's 1. Okay, so I'm gonna replace each of these with L. I'm not gonna do the whole taking the limit thing. I'm gonna say, oh yeah, I know this is gonna be L, that's gonna be L. And then I'm gonna solve for L. So I get L times L plus 3 equal to 2, right? Multiplying both sides by L plus 3. And then multiplying this out, I get L squared plus 3L. I'm gonna subtract 2. I'm sorry, I meant this to be different. I knew I wanted it to be 4. Sorry, I want this to be 4, not 2. Sorry. I knew I was doing the math wrong in my head. So that's what I've really got. Okay, L times L plus 3 equals 4. I've got L squared plus 3L minus 4 equals 0. And then I'm going to solve this by factoring. L plus 4 times L minus 1 equals 0. So I end up with, so I might have picked the wrong thing there. I get L equal to negative 4 or L equal to 1. So which one is the limit? Well, in this case, since we're starting at 1, we're starting at a point that's not going to change anything. Check this out. If you start at 1, and that's actually 4. If you plug in 1 for a sub 1, you get 4 over 1 plus 3, which is 4. 4 over 4 is 1. So a sub 2 is 1. If you plug in 1, you're going to get a sub 3 is 1, and so on and so on and so forth. So if you happen to start at the equilibrium value or at the limit value, you end up getting the same thing over and over and over again. If we had started somewhere else, like a sub 1 equal to 0, then it's a little more interesting. Then a sub 2 is 4 over 0 plus 3. And then a sub 3 is 4 over 4/3 plus 3. That's not quite as nice, but we can simplify that. 4/3 plus 9/3 is 13/3. So a sub 3 is 4 over 13/3, which is 4 times 3/13, which is 12/13, which is pretty close to 1. So it looks like I'm probably going to be bouncing back and forth between values that are below 1 and values that are above 1. Values that are below 1, if I plug in 12/13, it's kind of a pain in the butt, but a sub 4 would be 4 over 12/13 plus 3 is 39/13. So this ends up being 4 divided by 51/13, which is 4 times 13 over 51, which is 52 over 51. So just a little bit bigger than 1. So it definitely makes sense here that the limit is 1, not negative 4. So if you get more than one value for L, they can't both be limits, only one of them is the limit. And then you kind of have to look at what your sequence is doing to see which one makes sense as an answer. All right, 1 sec here. So those are some good difference equation questions. So let's talk about, someone said the squeeze theorem. Someone said, no, that's all, okay. So squeeze theorem definitely has to do with limits. And so yeah, I guess we can do the squeeze theorem stuff first. And so what I really want to get to after the squeeze theorem is talking about just kind of how you evaluate limits of a few different types. Well, mostly 0 over 0 types. Let's talk about the squeeze theorem first. So the squeeze theorem, here's what it says. And I have some good pictures to share with you guys. Squeeze theorem, I'm super lazy to write it. I can guess I could actually write out the words. So the squeeze theorem says the following. If you've got a function that's between two other functions, so if you have f of x between, say, g of x and h of x. And we'll do an example in a minute to kind of solidify this, and I'll show you the picture. So if you have this, and if the limit as x approaches whatever you're approaching, so if you say we're approaching a of h of x, if this is equal to the limit as x approaches a of g of x. So basically, if the outer things have the same limit as x approaches a, then the inner thing also has to have that limit, or get squeezed to that limit. So if these two limits are both equal to, let's call it L, then we get to say that the limit of the inner thing is also equal to L. Okay, so I'm gonna do something real quick here. So let me show you. I want to actually get rid of those first. Let me do another one. Yeah. Oh, that's crazy. Sorry, I'm going to show you guys a graph here in just a second. Well, let me zoom out though. So, okay. So I'm going to share my screen here. Let's share the screen. Yeah, come on. I always forget to click share. Okay, so here is the graph of the function sine of 1 x. And what I want to point out to you about this particular function is that the limit as x approaches 0 from either side does not exist. As you can see, as we get closer and closer to 0, the y values start just going back and forth and back and forth and back and forth between 1 and -1. You can zoom in and it just looks super crazy, right? And it gets, I mean, the more you zoom in, it's like, oh my God, woo, okay, fun times, right? But it's just back and forth an infinite number of times between 1 and -1. So the limit doesn't exist because as you get closer and closer to 0, the y values don't get close to one particular value. Sorry, I keep losing my pen. I keep putting them over here and I don't need to. So what I want to say is this. The limit as x approaches 0 from either side of sine of 1 over x does not exist. It's true from the right. It's also true from the left. Oh, sorry, you guys might not be able to see that so well because I'm sharing my screen, so I'm going to stop sharing for now. Okay, so that limit does not exist. And there's a way to show it like mathematically where you keep making values of x that are closer and closer to 0 and you keep making values of y that are either 1 or -1. I don't think we need to do that. I think the graph really kind of shows it. That's not so much what they care about. What I do want to show you is that although that limit doesn't exist, the limit as x goes to 0 of x squared times that thing does exist. So here's what I really want to show you. The limit as x goes to 0 of x squared times sine of 1 over x, I'm going to show you that that's equal to 0. And here's how we do it. So something that's useful to know, whenever you're dealing with a sine or a cosine function, you're always able to say it's between -1 and 1. And often that's kind of the key to success when you're doing a squeeze theorem problem, is recognizing, oh, I've got sine or cosine, and I know that sine of whatever is in there, it doesn't have to be just x, it can be anything. Sine of anything is between 1 and -1. And the anything in this case is 1 over x. It might oscillate a billion times before we get to anything meaningful, but it's still between 1 and -1. Now here's kind of the key steps. After you've said your trig sine or cosine is between 1 and -1, then you want to multiply every side of this compound inequality so that you get what you have here right there. So here, I have x squared times sine of x, sine of 1 over x. Here, I would like to have that. So what I'm going to do is I'm going to multiply everything times x squared. We're trying to write 2 times in one hand. So that's kind of the key step there. Is now the middle thing is the thing I'm trying to take the limit of. So here's what I've got. I've got -x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. And now here's what we're going to do. We're going to take the limits as x approaches whatever x is approaching in our original limit of the outer things. So say, what's the limit as x goes to 0 of positive x squared? Well, what can you do for this limit? Or how can you evaluate this limit? Anybody? Okay, you guys want to be quiet today. I understand. So the way you evaluate this limit is you can just plug it in. That's what we're going to see. He was talking about this in class yesterday. On Wednesday, called the direct substitution method. If you've got a polynomial or a rational function, or actually a lot of other functions, if you've got a polynomial or rational function, as long as it's defined, you can just plug in whatever x is approaching to get the limit. You can also do that for the other part, and the limit as x approaches 0 of negative x squared. Well, if I plug in 0, I get negative 0 squared, which is still 0. So then the limit of this is 0. The limit of this is 0. So the limit of the middle thing also has to be 0. So we say by the squeeze theorem, or the sandwich theorem is what he prefers to call it, whatever. The limit as x goes to 0 of x squared times sine of 1 over x has to equal 0. And that's very generally kind of how the squeeze theorem works. You find the function. You find a way of writing the thing you want to take the limit of between two other functions, and then you take the limit of it, of the other outer, take the limit of the outer things, and then you get the limit of anything. Let me do 2 more squeeze theorem examples. One of them which you did in class, but I feel like you guys should see it again because it's pretty important. And the other one is one that is fairly standard. So let's say I want to find the limit as x goes to infinity of 2 cosine of x plus, now let's write this. I want to write it this way. Apologies. X 5x squared plus 2 cosine of x all over 3x squared. I feel like we did one like this the other day, but maybe I'm just lying to myself. We might have done a squeeze theorem one like this the other day. It's fine to do another one. So if this was 5x squared plus so just let me remind you guys. If we had instead a limit as x goes to infinity of 5x squared plus 2 over 3x squared plus 4, what would the limit of that be?
5 over 3.
Exactly, right? It's a rational function. The degrees are the same, exactly. So here's the thing. Since cosine of x is between 1 and negative 1, you can say that this whole expression is between this expression with a plus 2 and this expression with a minus 2. So I'm going to show the work, but here's what we're going to get to at the end. We're going to get to the thing we're trying to take the limit of. It's going to be less than or equal to this plus 2 times 1. And it's going to be bigger than or equal to this plus 2 times negative 1, or that minus 2. Now, I certainly understand maybe not being able to see this right off the bat. It's taking me a while to really kind of figure out, yeah, that always happens. But here's the way you can kind of get there. You can start with cosine of x between negative 1 and 1. You can multiply everything by 2. So negative 2 is less than or equal to 2 cosine x, less than or equal to 2. You can add 5x squared to each part of the inequality. So 5x squared minus 2 less than or equal to 5x squared plus 2 cosine of x less than or equal to 5x squared plus 2. And then to get from here to there, you just divide everything by 3x squared plus 4. So 5x squared minus 2 divided by that is less than or equal to 5x squared plus 2 cosine x divided by that is less than or equal to 5x squared plus 2 divided by that. So that is always going to work. So if you have a limit to infinity, especially with a sine or a cosine, you really don't want to use the squeeze theorem. So then we still have to do a little bit more work. We have to say what the limit of each of these things are. So we know that the limit, look, I've saved myself some work. The limit of this is equal to, as you guys told me, 5/3. And we also know that the limit as x goes to infinity of 5x squared minus 2 over 3x squared plus 4 is also 5/3, right? It's the same sort of thing. The minus 2 doesn't change the limit. Sorry, I just pound my hand, which I hate. So then, since the limit of this is 5/3 and the limit of this is 5/3, the thing between the two, the middle thing, has to have a limit that's also 5/3. So we can say, sorry, I'm out of room here. So by the squeeze theorem, the limit as x goes to infinity, 5x squared plus 2 cosine x over 3x squared plus 4 also equals 5/3. That's what's going on there. All right. One more, because I know we talked about it in class the other day, and it's super important. Oh, shoot, darn. Before I erase this one, so I want to show you a picture. Apologies. So let's look back at let me share my screen again. So let me close this graph on business. So let me show you. So here's y equals x squared, and here's y equals negative x squared. And then I'm going to also graph y equal to x squared sine 1 over x. If we look at it, so it doesn't look real super clear here, but if we zoom in a bit, I'm going to make this wider. Sorry, 1 second here. So if we zoom in, look what happens. The purple function, which is the x squared sine of 1 over x function, is getting squeezed between x squared and negative x squared. As you follow along there, it gets super duper smushed, and it's got to get closer and closer to 0 because the upper one and the lower one are also getting closer and closer to 0. So hopefully that kind of helps you kind of see why this has to be true. I wish there was a way, I know there's a way you can change your y or x scale, but I'm not super great at this. So I think that shows enough that, oh yeah, we're definitely getting smushed down to 0. I should, let's see here. No, darn it. Anyway, that's all I want to say about that. So asymptotes, yes, we can also talk about asymptotes. So I don't want to talk so much about horizontal asymptotes because we've talked about that a lot. And I did, and so there's a couple examples on YouTube that I posted that I think you should go look at if you want some horizontal asymptotes help. We can talk about vertical asymptotes for just a hot minute. I was going to erase this. Oh, sorry. After we, so I still want to do one more squeeze theorem example. I'm going to save the asymptotes till the end. So the last squeeze theorem example I do want to do is one that's important. It's this one. It's the limit. You can either use x or theta or whatever. He used theta in class, but it's kind of standard. As theta goes to 0 of sine of theta. And so the end result here is that this limit is 1. In fact, again, if we want to graph things for just 1 second, we could totally graph it here and say, hey, what's sine of x over x look like? Let me close these other ones. Sorry, I'm not sharing my screen just yet. That's interesting. Oh, I need the y equals. Sorry, 1 sec. Or not. Anyway, that seems weird. I don't know why it's not graphing it. How strange. All right, 1 second. I apologize. I wanted to show you guys this graph, but it's not like coming up nicely. I don't know what the problem is here. That is strange. There's definitely a graph on this. Oh, I was zoomed in. I'm dumb. I was zoomed in too far. Okay, sorry. So let me show you guys this graph so you can see it. So here's the graph of sine of x over x. If we zoom, and it looks really like nice and continuous and well-defined, and it is everywhere except at the point 0, 1. So if you actually look right here, the function is undefined at 0, right? And that's clear, right? If you plug in 0 for x, you get 0 over 0, which is undefined. It also seems pretty obvious from the graph that we can say, well, hey, look, it seems pretty clear that the limit as x goes to 0 of sine of x over x is equal to 1, right? Just from the graph, we can totally kind of justify, oh yeah, well, clearly the right-hand side, the y value is equal to 1, the left-hand side, the y value is equal to 1. So it seems pretty reasonable. He did a proof of this in class, which I think was a little bit different than how it often gets done. Not a lot, like it's still pretty similar to how it gets done, but he did something slightly different. So I just want to kind of walk you guys through it again. I do think it's worth seeing just so that you really, really believe this limit is equal to 1. we do use this limit a fair amount. So here's the way we set this up. We're going to use the squeeze theorem, but we have to work hard to get there. So we're actually going to draw. So this is a sector of a unit circle, or as I like to think of it, it's a slice of pie. So it's a slice of pie of a unit circle, meaning the radius is 1. So this length here is 1. Oops. Ah, damn. Really was hoping I wasn't going to get red ink on the carpet. That's a bummer. That's coming out all right. Shit. Well, that's too bad. Oh well. Fuck. So that length is 1. That length is 1. And we label some points. I'm going to call this O, this A, this B. I'm going to call this angle theta. I'm going to drop a perpendicular here. Call this point P. Actually, I usually call it C. It doesn't really matter. And then actually, I'm going to draw another sector over here. I'm going to call that point C. Okay, so I'm going to use some inequalities about areas. So I think it should be fairly obvious just from the picture I've drawn that the area of this sector is less than the area of this triangle, which is less than the area of this larger sector. So I'm going to write that down. The area of the sector, which I'll draw like this. So sector OPC has less area than triangle OPB. And it has less area than sector OAB. Okay. So then we need a formula for each of those things. Now, we all know the formula. Hopefully, we all know the formula for the area of a triangle. It's 1/2 base times height. So this here is going to be 1/2 the length of OP times the length of PB. Now, the area of a sector is something you might be less familiar with. The way I kind of think of it, well, what's the area of a circle? The area of a circle is pi, wow, that's not how you write that, is pi r squared. But really the way I'm actually thinking of it, which I know is going to seem weird, is it's 1/2 times 2 pi times r squared. Because it's really 1/2 times the angle for the whole circle is 2 pi radians times the radius squared. And the area of a sector follows the same formula. It's 1/2 of the angle times the radius squared. Which makes sense, right? If the angle is, say, pi, which would give you half the circle, your area would be 1/2 pi r squared, which is 1/2 the area of the circle. So hopefully that seems clear. I don't want to get too into that, but I can talk about that later if you want. So for the bigger sector, it's going to be 1/2 times the angle times 1 squared. For the smaller sector, OPC, it's going to be 1/2 times the angle times the length of this, which I'm going to say is OP squared. And I know this might seem kind of like gibberish, but it is really kind of sensible to think about. So one more thing I need, in this triangle here, in triangle OPB, where the length of the hypotenuse is 1, I can say that, well, if this is OP and this is BP, sine of theta is the opposite over the hypotenuse, which is just the length of BP divided by 1. And cosine of theta is the adjacent over the hypotenuse, which is just the length of OP over 1. So I can replace in this equation OP with cosine of theta and PB or BP, sorry, same difference, with sine of theta. Here's what I'm going to get. I'm going to get 1/2. Well, actually, before we do any of that, let's multiply everything by 2. I'm going to just cancel all the 1/2s, multiply everything by 2. Then I'm going to have theta times OP, which is cosine theta, so which is cosine squared theta, less than or equal to OP, which is cosine theta, times BP, which is sine theta, which is less than or equal to just theta. Okay, we're almost there. I want to take the limit as theta goes to 0 of sine theta over theta. So the way I'm going to do that is by making sine theta over theta the thing that's in the middle of my inequality. So to get sine theta over theta, first I need to get rid of this cosine. So I'm going to divide everything by cosine. And I'm going to cancel one of the cosines there, one of the cosines there. But I'm also going to divide everything by theta. So now I've got this. I've got theta cosine theta less than or equal to sine theta less than or equal to theta over cosine theta. Then I'm going to divide everything by theta. Dividing by theta is the same as multiplying by 1 over theta. So here the thetas cancel, here the thetas cancel, and I'm left with the following. Cosine theta less than or equal to sine theta less than or equal to 1 over cosine theta. Okay, I'm almost out of room, but we're almost done. What's the limit as theta goes to 0 of cosine of theta? Oops. Well, again, when you're finding a limit, you can just plug in what you're approaching as long as it exists. So if I plug in 0, what's cosine of 0? You guys there? Anybody? Oh, you're so close. Sine of 0 would be 0. Cosine of 0 is the other value. It's going to be 1. Yeah. And so what's the limit as theta goes to 0? Sorry, I know it's super smushed in there. Of 1 over cosine theta. Well, cosine theta is still going to 1, so 1 over 1 is still going to be 1. But look, the limit of this is 1, the limit of this is 1, so the limit of sine theta over theta, sorry, the limit of this has to also be 1 by the squeeze theorem. So this limit is equal to 1 by the squeeze theorem. We will use that again later, so definitely try to keep it in mind. All right. So I think that's maybe not. I mean, so we use the squeeze theorem like here and there. It comes up every now and again where we want to really use it. It's not something, I don't know. It's hard to say how useful it really is. We use it enough that you should be familiar with it, but I wouldn't worry excessively about it. All right, so let's talk about limits. Specifically, sorry, this pen is driving me crazy down here. I know I can get it out. I feel like I should be blotting it, but sorry, I know. It's not a huge deal. It just looks terrible. Had to be the red pen. All right, so when you're evaluating 0 over 0 type limits, there are usually kind of 3 standard methods of attack. Well, aside from that, right? So for 0 over 0 types of limits, there are 4, well, there's a lot of things. One thing that can happen is you can have sine x over x, right? So the limit, we just did this, right? Limit as x goes to 0 of sine x over x is equal to 1. That's common knowledge now. You can just state that without having to do anything. And we'll kind of expand on this later, but I'll just point out, we can really say anything. So it could really be the limit as x goes to 0 of sine of anything that's going over to go to 0 over the same anything. So it could be like sine of 7x over 7x. And that limit would also be 0, would be 1, sorry. As long as the inside of the sine function is the same as what's down here, and they're both going to 0, then that limit ends up being 1. Then there's also lots of other things, like, well, what I call are the algebraic or the algebra methods. In fact, I'm going to leave this here. I'm going to go to the other side and come back and fill this in. So we've already talked about the first type. I still want to give you another example. One sec. Oh, in fact, this one is going to be a good example of talking about asymptotes. So I might throw in an asymptote on the side here. So let's say I want to find the limit as x approaches 2 of, sorry, I'm going to make something up now. X squared minus 5x plus 6 over, sorry, brain wanting to work, whatever, x squared, 3x squared minus 12. Cool. And you should always double check, because sometimes they just start trying to like fool you. If you plug in 2, do you actually get 0 over 0? Let's see, it looks like it, right? If I plug in 2 on the top, I get 4 minus 10 plus 6, yeah, that's 0. 2 on the bottom, yeah, 12 minus 12 is 0. So this is a 0 over 0 type. So now if I want to evaluate the limit, well, one of our methods for evaluating limits is kind of the most straightforward thing. It's to factor and cancel anything that makes us have a 0 on top or bottom. So if I factor the top, well, here's the thing that we should be aware of. If you're plugging in 2 and getting 0, it means that x minus 2 should be a factor. So I'm expecting x minus 2 to be a factor on top and on the bottom. The bottom I probably should wait a second, but I'm expecting that. On top, it's going to be x minus 2 times x minus 3. On the bottom, I'm going to factor out of 3 first. You're left with x squared minus 4, and then factor further. Sorry, give me equal signs, not those equal signs. So that factors further as 3 times x minus 2 times x plus 2. And now, we can cancel the x minus 2 factors. And it's okay to cancel those because the limit is concerned with everything near 2 but not at 2. So canceling out where this is undefined doesn't really make a difference. And then we're left with the limit as x approaches 2 of x minus 3 over 3 times x plus 2. And now we can plug in the value of 2 for the remaining x's and get 2 minus 3 over 3 times 2 plus 2, which is going to be negative 1 over 3 times 4, which is 12. So this is what I call the factor and cancel, or just factoring. So the first algebraic method, factor and cancel. I didn't say the cancel part because that's kind of always implied that you're going to have to cancel some stuff that's making you have the 0 on the top and 0 on the bottom. Okay. Before we move on to another example, I want to point out this function has actually has both kind of asymptotes. So we can talk about the asymptotes for one moment here. So this one, hopefully, it's easy to see that the horizontal asymptote is what? Oh shoot, I better forget, we're almost out of time. Sorry, I'll fill in the blanks. So the horizontal asymptote is y equal to 1/3. And you can either look at this one and say, well, yeah, the degrees are the same. So it's 1/3. Or you can even look at the reduced version, which is x minus 3 over 3 times x plus 2, and it's still going to be 1/3. For the vertical asymptote, you have to be a little bit more careful. So for the vertical asymptote, if we look at this expression here, you might mistakenly think that for y equal to x minus 2 over x minus 3 over 3 times x minus 2 times x plus 2, if you just look at where the denominator is 0 before you cancel things out, you're going to be making an error. It is not correct to say that there's a vertical asymptote at 2. There isn't a vertical asymptote at 2. because these factors cancel. So you have to cancel any common factors before you say anything about vertical asymptotes. So if I look at this function, which is now y equal to x minus 3 over 3 times x plus 2, except that we know x can't equal positive 2, right? It's not in the domain of the function. Well, then if I look at this, it still is true that negative 2 is a vertical asymptote, because negative 2 makes the denominator 0 and not the numerator. So you definitely would have a vertical asymptote at x equal to negative 2. And at x equal to positive 2, it's undefined, but it's undefined in the way that you have a hole. In fact, you can totally graph this one. So I really like, it's nice to graph on Desmos just because the graphs look nicer than what I can just draw really easily. So if I graph this one real quick, like on Desmos, here's what it looks like. It is, let's do some parentheses here. I guess you guys, maybe you should see what I'm doing instead of me just doing it and then like where did that come from? So I'm just plugging in, let's see, let's turn this one off. So I've got x squared minus 5x, I'm not simplifying it, plus 6, and then divided by 3x squared minus 12. And if we zoom out a bit, right, I'm too zoomed in here. So you can see, oh yeah, right there, there's a vertical asymptote at negative 2, like we said there was. But over here at positive 2, there is not a vertical asymptote. So I'm going to zoom into positive 2. Right, clearly not a vertical asymptote here. But if we look at positive 2, it's undefined. But the y value is about negative 1/3, because the limit, sorry, negative 1/12, not negative 1/3, because the limit as x approaches 2 is negative 1/12. So this graph would actually have a hole at the value of 2 comma negative 1/12. So that's something good to know about vertical asymptotes. You only get the vertical asymptote when after you've canceled any common factors, the remaining expression has 0 in the denominator. Okay, sorry, that's not what you guys didn't see. I mean, it's not like it's terrible, but okay. So that's one kind of, yeah, I think I can fit in the last two cases. So I'm going to give you guys 2 more limit examples, and then we'll talk more about limits on Monday. So there's 2 more algebraic methods that I think about when I'm finding a limit as x approaches some value. And so here's one of them. Let's say we have the limit as x approaches 3 of, let's make this not too terrible, x minus the square root of, 5x minus 6. Right, that'll work just fine, over 4x minus 12. And again, I will mention, this is definitely a 0 over 0 type of limit. You plug in 3 on the top, 15 minus 6 is 9, square root of 9 is 3, 3 minus 3 is 0. Plug in 3 on the bottom, you definitely get 12 minus 12. So when you have something like this, well, you can certainly factor a 4 on the bottom, but to deal with the top, you have to multiply by the conjugate. So the second method, the second algebraic method that I usually think about is multiplying by the conjugate. And then usually also factoring and canceling, right? There's always factoring and canceling after you do something, almost always. So here I'm going to multiply by x plus the square root of 5x minus 6 over the same thing. And I'm going to end up with, so the bottom part you should, or the parts that aren't conjugates, you should not multiply out. I should write this as 4 times x minus 3. But I don't want to distribute this with that because I know I'm trying to make that x minus 3 cancel. And distributing it's going to make it harder to see it cancel. I'm just going to write this. And then on top, I know we're going to multiply by a conjugate. The first thing squared minus the second thing squared. But the square root squared is just the inside stuff. Now I want to point out, I've actually made a small error here. It's got to be x squared, or this thing squared, minus all of this squared. So it should be minus all of 5x minus 6. All right. which is just, so I'm gonna, fine. So I don't think I'm gonna get to my last example here. You get x squared minus 5x plus 6 over the stuff on the bottom. And now we need to factor and cancel. So the top factors, this is actually the same thing we were doing last time. It's the limit as x goes to 3. The top is going to be x minus 3 times x minus 2. The bottom is still 4 times x minus 3 times x plus the square root of 5x minus 6. And finally, the things that are making us have a 0 on the top and a 0 on the bottom, when I plug in 3, the x minus 3's, those get to cancel out. And you can either, so some people like to do this in one shot, some people like to do two. You can either just plug in 3 for the rest of the x's, or you can rewrite it as the limit as x goes to 3 of x minus 2 over 4 times x plus the square root of 5x minus 6. And then plug in 3, and get 3 minus 2 over 4 times 3 plus the square root of 15 minus 6. That's going to end up being 1 over 4 times 3 plus 3 is 6. 4 times 6 is 20. So that's how you do one like that. And we're kind of out of time, but here's what I'll say. So next time, we'll finish off this list. The third thing on the algebraic methods is using a common denominator. But if you have questions about more questions about asymptotes, you should go look at the videos on YouTube. I'll try and get a quiz posted sometime before Monday. So my intention is to give you guys more time on the quizzes in general. So I'll try and get that up sometime over the weekend. If you have questions, feel free to start a discussion in Canvas, or you can always email me. But discussions are better because then everyone else can see the questions if they are applicable to everybody. So start a discussion if you think anyone else might be interested. But it's really just a private message from me. Welcome to email me anytime. So I hope you guys have a nice weekend full of not too much math, and I will see you all on Monday. Take care. I'm going to end the video. Oh, and make sure you fill out the attendance form once and only once, please. I'll leave that up for just a second so everyone can grab it if you can grab it there. Okay, I'm really ending the video now. Here we go. Goodbye. Goodbye.